So we've seen how we can put together acquisition of images with um, some of the machine vision VIs, in particular the count objects VIs, so that we can find an object, determine its XY position. Now, in this front panel of this VI, I'm going to show you how you can actually extract that XY position. So I'll show you the actual VI shortly, but you can see it has the same VI that we've seen as far as the acquire and count objects. And what I'm going to show you is how to add a couple of other things here so that you can build a VI that can control the meter and position this bob at different locations. So let me bring up that VI. So here's a front panel. I'm gonna show you how to play around a little bit with the settings, not too much, but at least to give you an idea of how to do that. And first, let's look at let's look at the front panel. Again, this is the same as what we've looked at before. It's got the image. Obviously it's run from a previous case, the count objects, and it's found an object here at the center. So the settings have already been set. I'm going to change them and let you see what happens. There's two other items that I added, and they're right here. One is you need to give it the vertex position, which is where is this center of rotation, and also what's this zero position here. I'm going to show you how you can use this little, and I call this a setup and calibration VI. It sets up the system, lets you adjust these values so that then you can also put within this VI a sub VI that finds, based on the actual new position XY, the angle of deflection from the zero and also the needle length. Measuring the needle length is not essential, but it's kind of a double check to make sure everything's correct. And note that it also has a user input for the input voltage. I'm going to show you how to do that. And there's a MyDAC connection connected in the system. And this is going to plot the position over time. It's just going to be continuously scrolling. So this is a setup VI that you can use to run your open loop tests and also to measure your system. So this is something that you ultimately could build in the lab for yourself. Let's look at the block diagram and focus first on this side. There's actually 4 or 5 pieces I want to show you. 1, 2, 3, 4, 5. And then there's some other little pieces I'll show you. But first, this is really just the setup for acquiring images. So you only have to do this once. Note that it's outside of this control and simulation loop. Now I've brought a control and simulation loop in here. You could also do this with a while loop. The reason I'm using a control and simulation loop is because we can then transition this to use it as a control type for controller type applications. One of the really nice features that NI has built into the control and simulation loop is that you can bring in, you can bring in vision VIs, you can bring in data acquisition and control VIs as well. You don't have to just use control and simulation in here. Now, control and simulation won't work outside of control and simulation, but some of these VIs can be brought in. So note, you set up the acquisition, right? You open the camera, you configure grab, you start a grab, and then you select your region of interest, and then you enter in here, and this is going to run every time step, right? Going to run everything each time step, but it's going to grab an image, cast it into gray, and then find the object, and then it analyzes the object. We'll talk about that shortly. So the other thing it does before it enters the control loop is it sets up analog out, sets it at 0 volts, then when it enters at every time step, it allows the user to change what is the output voltage on the analog output channel that you're looking at, right? So you got to make sure that you set this correctly to the analog output channel of interest. So note that then at the end of this, when you stop the control simulation loop, it stops the camera and closes it. Also, it sets the output voltage to 0. But one other thing, if you right-click on here, you can see the simulation parameters. They're not, I didn't extend this here, but I've set final time to, initial time to 0, final time to infinite. That way it just runs all the time. I'm using an order integrator, and it's going to run continuously until I tell it to stop. Right? Again, this note here says that. What else? Okay, so we want to talk a little bit about, okay, this object's determination now is giving us this data. I'm just going to remind you that what that gives you is an array of all the objects. You want to set up your vision so it only finds one object, and that's a 0th object, the first object. So that's what's happening here, is the array is being stripped of that one element of the array, which is the first object. That object information, this little cluster in here, is going to have all this information: object center, bounding box parameters, dimensions, the area of the object, orientation, so on. What we care about is the object center, so you can use this unbundle by name. That can be found under here in the cluster, class, and variant menu. And you can specify, I want the object center, and now this little cluster here has the XY data, and then it can go into this little sub VI, which is called find angle. This is a custom VI that you'll build using your geometric parameters for the 3 points that you measure. The vertex and the XY points are fixed, but the object center is constantly changing, and then based on that value you can find theta and needle length. Okay, so very basic VI. Let's see how it runs. As I said, you can adjust these after we get going, and I'll show you how this operates. Keep this brief. So again, you run this, it acquires, starts with the camera, acquires an image, and right away says, hey, find an object center. So now we want to find that 0 point. So you can do this by just selecting a region of interest here. Say OK. So now it's going to find that point 0 there, right? Do I have the correct vertex and x0? I can actually check that, because I can come in here and I can just look right over the vertex. I can put my cursor there, and there's a little bit of error here, but 327, 348, that's about what I've got there, right? 329, 350 is close enough. The 0 point, actually, you can, if this is running, you can read that from here. Note the 0 point is being read as, since I have 0 voltage, that's my 0 point. 245, 250, that's what I have there. So I'm at 0 angle. There's a little bit of noise fluctuation there, because this is fluctuating because of the possibly, if I maybe get, what is the let's play around with this. Let's see if I can fix that. See, so if you fix the threshold a little bit, it seems to be right on the edge. You can almost take that noise away. Maybe we can even go a little bit higher. And now, see, it's sitting a little bit more consistently. And now my 0 is at 246, 245, so I'm going to adjust that. Note that so now I've got a nice flat, very close to 0 angle there. Okay, you can tweak these a little bit more and get better zeros here. But that's it, right? Maximum object size, sometimes you want to play with that if you want to tell it to ignore certain objects, if there's more objects in the way, and I'm going to try to keep this brief, but you can play around with these different limiters here so it doesn't find objects that are obscuring your, the main point. Remember, you only want this to be a 0 point because of the way you're analyzing the data. Okay, so now you can adjust your input voltage, and this guy will move, and now you've measured the angle, and you can see that that's popped up to about 14 degrees. 2, 3, right? I have it limited to 5 volts in input. Go back down to 0. So you can see this meter has some dynamics, and we'll look at that a little bit more in the next lab. So I'm going to stop this. So what you can do now with this VI is you can take some data, V versus theta, and build this little model. By the way, I have a little typo here. So this little correlation, it shows angle versus voltage, but when we're building a little open, when you're trying to determine, say, I want to be at a certain position, you want theta on the right-hand side, and you want kV over theta. So this is a little typo here, should be V over theta. And that's actually correct here. It's the inverse of this value here. So that V over theta, if I tell you, hey, I want to be at 20 degrees, what should that voltage be? This model will give you that voltage now that you've calibrated this in a sense. So you've built a static model, an open loop model. And the way we can use that is now to kind of build an open loop controller. I can tell you, hey, I want to specify a desired angular position. I want you to use the static model to compute the open loop control voltage. You use that equation, and then you send that voltage command to the analog out, and then you can position this at certain points at certain times. And here's an example of how we've done that. A little white dashed line shows you the desired position over time. You can use a formula node to implement that, and the TA may give you a specified path that you want to follow, and then your open loop model will tell you, hey, what the voltage should be, and then this red line shows the actual measured response. Okay, you can also compute the error to see how far off you are from there, and so you can see I've got a little bit of an angular error here, at least for when I run these experiments. Okay.